Just trying to give people a little bit of time because we're a little low on people today. Hopefully it's not. I know Zoom isn't perfect, but hopefully I think we got a little bit better sound quality now. Hopefully I plan to be back in the classroom on Wednesday and Friday this week. I haven't had a fever yet today, so I think we should be good to go. I feel back to normal finally, and wholly expect to be back in the classroom Wednesday and Friday. So what we'll do, I believe, this week should have been, so last week should have been that group 2 showed up Monday and Friday, and group, give me 1 second. Group 2 should have been showing up on Monday, Friday, and group 1 would have been showing up Wednesday. So what we're going to do this week is try to follow that format. So group 1, if you could show up Wednesday, and group 2 show up on Friday, okay? And then the next week it'll be the same thing. It's just that group 2 would be on Monday, Friday, and group 1 would still be on Wednesday. So we'll kind of keep it consistent for the next 2 weeks. But we missed Monday this week, so it's not like group 2 is getting an extra week of 2 classes. So Wednesday, Wednesday, group 1 this week, and Friday would be group 2. Okay, and I'll post an announcement on Canvas just to clarify this. Let me make sure I'm getting everybody in here. All right, so hopefully either on Friday or today or sometime over the weekend, you were able to listen. There's about a 20-minute long additional kind of lecture, just introducing the idea of probabilities, how we start to think about them, relating them to the relevant frequency stuff we've already talked about. And so hopefully you get a chance to look at that. And I left off, I was just about to start talking about probability notation. So we'll kind of pick up with that today. So what I'm going to try to do with this is leave the video open for this first part down in the corner and do some work. So if you can't see anything or you have a question on what I'm writing down here, let me know, but it should follow along with kind of the slides and I think make them make a little more sense and give us an idea about what this notation really means, okay? So the first thing we're going to talk about is the complement of A. So A complement is just written A with this kind of superscript C, right? So we'll kind of use this event A for every example that you look through. So let's say that we're thinking about the experimental outcome space for rolling a die. So our event A is a subset of that, which is just seeing a 2 or a 3, right? Both those outcomes are in event A. Right? So if that's the case, a complement is just every other outcome not in A. So that would be, I could see a 1, I could see a 4, I could see a 5, or I could see a 6, right? Those are all the possible outcomes from rolling a 6-sided die that are not in A, okay? That's all the complement means. If we want the union of 2 events, so now let's assume I've got this event B, and the outcomes in that space are 3 and 4. And these squiggly lines are just kind of like, this is what's in the set. We don't have to worry too much about that. Hopefully that it's kind of clear that that's what those are. But event B here is just that I roll either a 3 or a 4. So if I want the union of those 2 events A and B, I write this as, well, not even probability, sorry. A union B. So this is A union B, or is it in A or B? Right? Is it in either one of them? Right? So if I think about here, the union of A and B, or is it in A or is it in B? And it's just kind of this U. It's really a set symbol, but for the sake of what we're doing, you can think of it as a U, right? So if it's in either A or it's in B, it could be a 2, it could be a 3, or it could also be a 4, right? 2, 3, 3, 4. If I look at all the possible outcomes there, 2, 3, or 4, each one of those numbers would be in either A or in B, okay? So that's my union of the 2 events. And then a intersection B, so A intersection B, or A and B, means is it in A and is it in B? And some people say you can kind of remember it's like this upside down U, which if you kind of put a line, kind of looks like an A, right? But this upside down kind of U or set symbol means is it in A and B, or A intersection B, is another way of saying that. Well, here, what's the only outcomes that are in both A and in B? Well, the only outcome here that's in both is actually 3. Oop, I can get that glare off the screen there. Right. So that's kind of walking through that different set notation. Right. So that when we did the intersection there. So that's the way we can think about these first 3. So the fourth one is a little bit different. And for now, I'm going to introduce the idea and not go as in depth as we will Wednesday into it, but the idea of a conditional probability, and hopefully just to double check, actually, so let me make sure that the recording is going here. Yeah, okay, we're going. Everyone can hear me okay and everything, right? I meant to check that before we kind of dove into things. Hopefully someone lets me know. All right, awesome. So this one is this is a conditional line, right? Or a conditional probability we'll start talking about. So what this vertical line means is whatever's on the right-hand side of it, assume that it's already occurred. Like for sure, guaranteed, it's occurred. Given that information, now what's the probability that A occurs, right? So this is the example I usually use for this is something like, if I'm just interested in the probability that I walk outside and I slip and fall, pretty low. So if the event A is I walk outside and I slip and fall, pretty low probability. If I then tell you, but given that B has occurred, and the event B is that it's been, raining / icing, it's, right at like 30 degrees, and it's real icy out. Well, now what's the probability, right? Now that I know that information that event B has occurred, that it's icy out, now it's a probability I step outside and fall. It's a lot higher, right? So it's this idea that having additional information can influence the probability of whatever you're looking for, right? So we'll talk about conditional probabilities more on Wednesday, but this will be kind of the notation is where this vertical line is, whatever is on the right-hand side, that you're assuming that that has already occurred. Given that B has already occurred is essentially the way you read that, okay? You can kind of think about, and in this example, if I roll a die, what's the probability that when I rolled it, it's a 3? Well, I don't have any other information. There's only 6 options, so it's 1/6. But if I think about, given that A has occurred, what's the probability that I rolled a 3? Well, now I'm at like a 50-50 split. So if I know A has occurred, I know either a 2 or 3 was rolled. It's just, I've limited my space now. It's not 6 possible outcomes. Once you tell me that given that A has occurred, well, now I know there's only 2 possible outcomes that could have occurred, and it raises the probability of seeing 3 there. So that's kind of the idea of a conditional probability. So I'm going to minimize myself real quick. We can see these different displays of some of the things we're talking about. So let's say I looked at each one of these Venn diagrams. This rectangular area represents every possible outcome for whatever experiment you're looking at, right? So if it's rolling a die, it essentially includes every single possible outcome I could see. 1, 2, 3, 4, 5, or 6. It shows that entire space. So if I add up the probability of every possible outcome, I said this in kind of the additional video, they have to add up to 1. Right? If I take every single possible outcome and I add them all up, the probabilities they have to add up to 1. So this rectangular space is meant to represent every single possible outcome, so we can think about that probability is 1. The area of that rectangle is essentially 1. You can think about it that way. So if I have different events that occur within that space, right? So even if it was just rolling the die, event A was seeing a 2 or 3, here's my event A, right? This circle represents every outcome that is within event A. Everything in this circle represents every outcome that's in event B. Where those 2 circles overlap, well, that means that it's in A and it's in B, right? It's in both events. And so A and B was that kind of downward or that upside down U, right? A intersection B or A and B. So this is our intersection where these things overlap. If I think about the shaded area over here, well, that's everything that's in either A or it's in B. Now notice the union includes the intersection, right? It can be in A and not in B. It can be in B and not in A, or it can be in both, right? So the union, or is it in A or is it in B, right? It can be in either circle or it can be in both. That's the visual representation of that. All right. Sure the chat's going to, okay. So the next thing we'll talk about is our contingency tables and how we read contingency tables. So let me make myself a little smaller here, but I'll still keep living down here in the corner. So the way in which we read these contingency tables are these top 4 left cells always represent intersections, right? Or those upside down U's, right? And what are they the intersections of? Whatever the row and column headings are. So this 0.4 is the probability of the intersection of A and B. 0.3 here is the probability of the intersection of A complement and B complement. And then so on and so forth, right? So that's how we read those top 4 left cells. They all represent intersections. The total columns, or the total row, I guess, down here, represent the probabilities just of the events themselves. So the probability of A is 0.6. Probability of A complement, 0.4. Probability of B complement, 0.5, right? So that's how we kind of read the totals. They just give us the probability of just one event. No intersection, union, nothing, just the one event. But the top 4 left cells, we all read as the intersections of whatever their row and column heading are. All right? Hopefully that's pretty clear. Now, one thing we can do, if you notice, if I'm looking for just the probability of A, I know that that is 0.6. But notice if I add across the row here, 0.4 and 0.2 actually add up to 0.6. 0.1 plus 0.3 is 0.4. 0.2 plus 0.3 is 0.5. 0.4 plus 0.1 is 0.5. If I add down the columns or across the rows, that's how I was getting these totals. So if I left these totals blank, you could add across the rows or down the columns and get them. So why is that the case? Okay, so I'll try to give you a pretty nice visual of why that's the case. So the 2 things that we have there, I'm telling you that this is true, and I'll try to prove it to you, but right, this is the probability of A and B. This is the probability of A and B complement. So I'm going to write those 2 things down here on the board, and then I'm going to draw you a larger picture. I'll kind of put the slides away. But those are the 2 things that I'm telling you these add up to. If I add these 2 together, these 2 things should add up to just the probability of that. Actually, I'm looking at this backwards. Why did I do that? My addition sign needs to be over here. So let me stop this here. So that's what we had on the table. I'm going to give you hopefully a visual representation of why this holds. So here's my experimental outcome space. So let's say I've got, here's A. That's my event A. I then have my event B over here. So this area represents what's in both A and B, or this is the probability of A and B. Okay. If I try to say, okay, well, what's left in my circle A? Well, this is everything that's in A, but not in B, right? B complement would be like, here, let me see if I can show you this way. B complement is like everything not in B, right? Everything outside of B. So that's B complement. So where does B complement overlap with A? It's kind of this half moon over here. Well, saying they overlap is really just saying that's where A intersects B complement. And sure enough, we said if we added those 2 things together, right, we should get the entire circle of A, or the probability of A. So that's where that comes from, right? That's why we can add across the rows or down the columns, because the intersection of an event with another event plus the intersection of the event with that other event's complement should always add up to just the probability of whatever that event was we were looking for. Sorry, I was trying to find my marker cap real quick. Okay, so let's go back to the slides here. Any questions on that before we keep moving? Also, just a random, I mean, you guys want to help me out in the chat a little bit just to get a couple answers. Do you like the, I guess put yes, if you like, do you like seeing me do kind of like that board work, more like that, or switching over to that overhead cam once we're back in class? Overhead board or sorry, overhead or kind of that board. I might start bringing this board to class and sitting more if that helps. The whiteboard does, it looks a little clear. Yeah, so I think I'm getting whiteboard. So I think I'm gonna start bringing that to class. And so if you're in class, I apologize, I might be sitting a little bit more just so when I do that, because I'm not sure I'm gonna be able to hold it up and kind of look down and figure it out, but I think that'll work a little bit better for us, especially the glare in here is bad, and in the classroom, I know it's not near as much of an issue, so we should actually be able to avoid that a lot more. So, all right, awesome. I'm glad that looks good. Okay, same thing works. Like I said, you can add across the rows or down the columns. It doesn't matter. I mean, once you have the totals, you don't have to keep adding up these intersections. You're going to have the totals there for you. Not that big a deal. Hopefully by now, if I asked you for the probability of A intersection B here, I've tried to be selling this a lot, but right, the intersections are just these top four left cells. So the probability of A and B, or intersection B, A, B, 0.4. I wanted A complement, B complement, A complement, B complement would be 0.3, right? So maybe I can get this mouse to work. Oh, there we go. Okay. I could really find any intersections of those row and column headings. So this one's a little bit trickier. So if I've got the union of two events, I'll show you a way right now, and then towards the end of class, I'll show you a different way to think about the union. But if I had this contingency table, I'm gonna show you how we could break it down to be a little bit different, so that the union's pretty easy to find. Okay, so let's get rid of this. So let's say we've got, switching colors here because that one's starting to die on me, I think. Oh man, that one's bright. So we've got, we want the union of two events. So I'm going to take A over here, and I'm going to take event B over here. Okay. So everything that's not in B, but in A, right? So everything that's not in B, but it's in A, is kind of this half crescent moon here, right? It's in circle A, but it's outside of circle B, that green circle. And everything in circle B, but not in circle A, is kind of this area right here. So what does that mean? So everything in circle A, but not in B, is the probability of being in circle A, and not in B is really just saying B complement, right? Everything that was in circle B, but outside of circle A, so everything in circle B and not in A, or an A complement, that was that component. And then what is the third part that makes up the union? Because remember, the union was just like the area of, is it in either one of these circles? So the area in the middle, well, that was just the probability of the intersection of the two events. Right? So we've got these three components that we can break the union down into. So if I go here, 1 second. So I have these three components. So the very first one I want is the probability of A and B complement. So the probability of A and B complement is 0.2. The next thing I wanted is the probability of A and B, that's 0.4. And then the third thing I want is the probability of B and A complement, which is 0.1. So if I just take those three components, add them all up, I'll have the entire space of what's in either one of these circles, or A union B. Right? So really, if I take those three values, add them up, that should give me the union, right? And this is kind of the reason as behind why, right? Because I can take that union and I can break it down into like three different parts of that union, and each one of those parts I'm able to find in that contingency table, right? Now I had to have a little bit of foresight to know I could do that, but once you know that you can do it, it's always going to be the same. It doesn't matter if the circles change a little bit, and so you should always be able to use a contingency table to find that union in a similar format. Now, instead of memorizing those three components, because the column and row headings can change a bit, this isn't the most technical way to remember it, but it always works. Whatever you want to find the union of, right? So A union B, you can always go to wherever the intersection is and then make an L, and that'll give it to you, right? So like if I wanted the probability of A complement, let's see, I can do this. I wanted the probability, oh, that's way too big, hold on. If I wanted the probability of A complement union B complement, I would go to the intersection of those two things, 0.3, make an L, and add these three things up. All right, so 0.1 plus 0.3 plus 0.2. Similar to how we did it when we were just looking for the union of the two. It's just you go to the intersection of wherever you found the union of, and then you make an L, add those three components up. Now, like I said, that's not a technical way to do things. That's not ideal. And so by the end of the class, I'll give you, using one of our probability rules, I'll give you what I think is a much better way to use the contingency table to find a union. Okay? But for now, that way works too, right? So just a sample question. I probably could have put this in a different order, but hopefully by now, even if I change the row and column headings, we're okay with finding these intersections, right? Or this R1 intersection C1, R1 and C1. Okay? So if I go the intersection of R1, C1, that's just this 0.4. It's as easy as we have. The top four of those cells all represent intersections. I'm going to keep hammering that, right? If I wanted the intersection of, right, R2 and C2, 0.3, which I now realize I should definitely change these to D1 and D2. So I could do like the intersection of R2, D2. Any Star Wars fans out there? All right. Anyways, so hopefully we're okay with finding those intersections pretty easy. So one thing I wanted to mention at this point, whether or not we're talking about intersections or unions, doesn't matter. It doesn't matter which way we order them, right? So saying that A union B or B union A is the same thing, right? If I said, is somebody over 30 or have brown hair, is the same thing as saying, do they have brown hair or are they over 30? Doesn't matter which order I say it in. Same thing for the intersection. It doesn't matter if I said, you know, you choose your two events. Is my dog smart and very black, or is my dog very black and smart? Right? Either way doesn't change it, right? I use that example because he's sleeping over there. That's how I got that one. So it doesn't matter the order in which we say things, which will come into play a little bit more on Wednesday when we talk about the multiplication rule and independent events. But for now, hold on to that in the back of your mind. And kind of thinking about those intersections, right? I always like this one to just throw it in there, break up things a little bit. When you say it's fine, when it's actually fine, right? The intersection there, the probability is like 0.01 or something. So you can always use Venn diagrams to make jokes like that, or dad jokes like that, I guess. So this complement rule, I think this gives like a really nice visual. We're getting rid of event B to make this point, because once we just have event A, I think it's pretty clear. If I took everything that's in circle A, and then I took everything not in A, right? A complement, it would be all this shaded blue area. Well, everything not in A fills out the entire rest of the experimental outcome space. So when I take A plus A complement, the areas, that adds up to the entire experimental outcome space, which we know is 1. So the probability of A plus the probability of A complement is going to always give us 1, right? So all I did there to get that complement rule was, oh man, all my markers just fell. All I did there was probability of A plus the probability of A complement is equal to 1. I then just rearranged my equation a little bit. I subtracted the probability of A from both sides. And what I was left with is, if I want the probability of a complement, it's always going to be 1 minus whatever the event is. And this is just the equation that's in the slide, right? That's our complement rule. And that'll pop up a lot, and it may seem really intuitive once we get going into some later stuff, but it really does go all the way back to this law, which if I take the probability of an event and its complement, that will always add up to 1. I could rearrange that equation a little bit to make it a little bit easier to deal with, but that'll always hold. Okay. Any questions on that before we keep moving? Check the chat here. So the next thing we're going to do is, I think, a easier or a better way to think about finding the union using a contingency table. So the addition rule, right, is going to be that if we want the union of two events, so I want the union of A and B, or A or B, if I just simply add the probability, oh, come on. If I just simply add the probability of A, or circle A, to the probability of B, what I've done is, what's in the middle here, which is the intersection of the two, I've actually double counted that. All right, so if I double count something, how can I make sure I only count it once? Well, I can just subtract it out one time. If I double counted it, subtract it out once, and now I've only counted it one time. So the addition rule is that if I want the union of two events, I can simply add the probability of those two events together, but then I have to subtract out their intersection. Because when I added up the probability of both those events, I double counted what was in both. And a good way to think about this, if you go back to the very first example we started out with, where events A and B were, did I roll a 2 and a 3? Or event A was, did I roll a 2 or a 3? Event B was, did I roll a 3 or 4? What would the union of those be? Well, we said it was 2, 3, and 4. If I just had written down every single number, I would have 2, 3, 3, 4. I'd have 2 3s. That doesn't make any sense. It's only one number, so I kind of like subtract it out once. It's not perfectly right, but it's a good way to think about it, right? I double counted, I need to take one of them away. That's what we're doing here. If I just add the probability of the two events, I've double counted what's in both, and so I need to subtract out that intersection. Okay? Did I hear someone try to talk? Did someone question? Okay, just making sure. I didn't want to. All right, nothing up there. Now, another way I can think about this, I don't think it's as, doesn't always click as easy with people. I could also think about breaking this down into 3 components once again, right? If I just want this crescent moon here, well, that's everything in A except for the part of A that's intersected with B. So I could take the probability of A and subtract out the intersection, and that gives me like this half crescent moon here. I could then go over, find this half crescent moon. Well, that's everything in B, except for the part of B that's intersected with A. So probably B, subtract out the intersection. I then have these two parts. I need the third one. So I then add in the intersection. These cancel, and I rearrange a little bit. I've got the exact same formula. I don't think this way never really connected with me. Maybe it connects with some of you a little bit better. I always thought the way of thinking about if I just add them up, that I'm double counting something. So I need to subtract it out once. That way always just clicks. I feel like it clicks a little bit easier with me and a lot more people. But if this way kind of makes sense as well, that's fine, because you still arrive at the same place, right? You still arrive at the same equation. So, all right. I want to relate this now, and I'm going to pull a slide down so I can bounce back and forth between it without having to scroll too much. Oh, where the hell is it? There it is. So let's go down. Right here. I want this to be right here. Okay. So if I looked at that addition rule, and then I go back to my contingency table. So we said before, we could just like make that L or break it down to 3 components, add them up. We got 0.7. 0.4 plus 0.2 plus 0.1 is 0.7. If I use my new rule, I know I can find the union by simply adding up the probability of these two events and subtracting out the intersection. So I'll go down here. The probability of A is 0.6, the probability of B is 0.5, and the probability of their intersection is 0.4. So if I go back to my equation, I just plug in the values that I just grabbed from that contingency table. So 0.6 plus 0.5, subtract 0.4. There I try to draw the plus and minus sign. There we go. Well, now I've got everything I need to solve for what that union is, right? So 0.6 with 0.5 is 1.1 minus 0.4. Sure enough, I get 0.7 that way as well. And to me, that just makes it a lot easier using this equation. Once I know this equation is going to always hold, it's a lot easier to just find the probability of A, the probability of B, subtract out the intersection as opposed to like drawing it, breaking it down. Oh yeah, this is the intersection of A complement and B, B complement and A, the intersection, add them all together, or find the intersection and create an L, but do I go this way? Wait, which way do I, just like, to me, it's a little bit easier to use that equation. But whatever way is easiest for you to find the union, you can use. That's just a different way of doing it. Okay? Yeah. Oh, we're plenty of time. Any other questions on that before we keep moving? Okay with that? Okay. So here we've got a definition of something. Now that we're thinking about this equation, we're thinking about intersections. I've probably already used this. I use it in my everyday life, probably too much as well. But the idea of things being mutually exclusive, meaning they can't happen at the same time. That's a layman's, really easy definition of it. A and B are mutually exclusive events if they can't happen at the same time. Excuse me. So it's like if they can't happen at the same time, it means there's no overlap. So we think about that Venn diagram. It's like, I'm gonna move myself out of the way here. It's like there's no overlap in A and B. That means their intersection essentially is 0, right? They can't happen at the same time. If something can't happen, the lowest probability, it means that it will never happen, and the probability is 0. So if the intersection of two events, right, they can never occur at the same time, there's no intersection, then the probability of that intersection is 0, right? They can never occur at the same time. So that's a pretty easy definition, I think, of mutually exclusive, just that if two things can't happen at the same time, there will be no overlap, so the intersection will just be 0, right, of those two events. Now, if the intersection is 0, notice finding the union is a lot easier, because now I just have to add up circle A to circle B. I've double counted nothing. Right? Nothing's been double counted. It's a lot easier. So this is kind of our main definition of are things mutually exclusive, right? And if that's the definition, that the intersection of the two events is 0, what would have to be true is that the contingency table, we'd have to see a 0. Because remember, these top 4 left cells all represent intersections. And so that would mean that the intersection of those two events has to be 0 if they're mutually exclusive. So you'd have to see a 0 in the contingency table, right? So if you don't see a 0 in the contingency table, then they're definitely not mutually exclusive. Right? That's an easy way to think about that, an easy way to check that. Okay. What I want to say? Oh, because the example I was pull back is right. Phone and internet access are mutually exclusive in the 90s, right? You had to use the same phone lines, so you could only either be on the internet or on the phone, unless you were fancy and had 2 phone lines at some point, right? So it's 2 things that you can't use at the same time. Those would be mutually exclusive, right? They can't happen at the same time. Okay. Let me see if there's any questions. That's pretty easy. So the last thing I want to kind of talk about for the rest of class, we'll kind of focus on this. So just for now, I guess, trust me. If you just accept, and I'll prove, I'll give you a really good example why, or proving to you why this is. But let's say we think about everything in this white area. We know that's the union of A and B, right? It's this white area is everything that's in A or it's in B. Could be in both, but it's in at least one of them, right? So we've got the union of those two events. That's that white area. if I added to that the blue area here, everything not in that union, well, I'd have filled the entire experimental outcome space. So I know those two things have to add to 1. If you trust me for now that the area outside that union is the intersection of the complement of the two events, then those two things have to add to 1, right? That blue area, which I'm telling you is the intersection of the complements, and the shaded white area, which hopefully at this point we can kind of recognize as that's the union of the two events. Those two things have to add to 1, okay? So we can go a step further. If we go back here, if we know that the union is just made up of these 3 things, right? Adding up the probability of the 2 events and subtracting out what we double counted, well, we can just put that equation and kind of plug it in here. So we replace the union of the 2 events with the probability of each event added together minus what we double counted, which was the intersection. And of course, we haven't replaced anything here, so that's still in our equation. So if these 2 things had to add to 1, we know that these 4 things will also add to 1. And now if we know any 3 of these components, we'll be able to find the one that we're missing. And this kind of makes sense. Like I'm more likely than not could probably find, I would probably be given the probability of A, B, and their intersection, but I might not be given the intersection of their complements, right? And so if I'm thinking about this, if I have any 3 pieces of information, I would have 1 equation, 1 unknown. I could use a little algebra to solve for it. Right? And I'll work through an example here in just a second, but I want to give you a little more intuition as behind why this shaded blue area is the intersection of the complements. Okay? So go away here real quick and come back. All right, so we need 2 different colors here, so hopefully these show up a little bit different. So let's say, I'm gonna use the green one or purple. So I've got my experimental outcome space. Here's A. Now where would A complement be? A complement would be just everything not an A. So I'm gonna just draw straight lines to kind of shade in everything that's not an A, right? So these lines represent A complement. I meant to leave a little space in between here. If I then think about B, so here's event B, what's everything that's not in B? Or what's B complement? Just those lines. So if you're looking, there you go. So we're looking at this, you can kind of see there's parts where there's purple lines here, but there's no green lines. There's green lines here, but no purple lines. Everywhere the green and purple lines kind of intersect, well, the lines just represent A complement and B complement. So everywhere where they intersect is really just the intersection of A complement and B complement. So that's really just everywhere outside of those 2 circles. So that's why the area outside of that union is the intersection of the complements, right? This is kind of like a pretty nice visualization as to that. I'm sure I could be a little bit, if I was better at drawing, shading, I'm sure maybe I could do a little better job showing that, but hopefully that kind of gets the point across. Right? All right. So that's a good representation of that. And I had that slide. I thought maybe, whatever, we're at a different order than I thought we were going to be originally, so we can skip that slide for now. We'll talk about that on Wednesday. So with this in mind, this equation in mind, let's say I gave you something like this, right? Where I tell you the probability of A, I tell you that this intersection of the complements, or kind of this light blue gray area, I tell you that's 0.3. I tell you the probability of the intersection of A and B is 0.1, but I don't know what point, I don't know what, I'm stuttering bad. I don't know what the probability of B is here, right? So I have these 3 pieces of information, but what I do know is, I know that the union of these 2 events, these 2 circles, plus this shaded gray area outside the circles, have to add up to 1. I know the area in the circles is just the union of the two events, which can be written as the probability of A and B, add those together, and subtract out what I double counted, which is the intersection. So what I really could do is go back and say, okay, I know the probability of A is 0.5. I know the probability of A intersection of B is 0.1. Intersection of the complements is 0.3. Let me go back to this equation, just plug those in. I know the probability of A, I know the intersection of the two, and the two events, and I know the intersection of the complements. So really all I'm going to do there is just start plugging my values in, right? So if I go down, so this is the equation I'm going to be using, right? Actually, I think we probably got enough time. Yeah, we got plenty of time. So I'm just going to write this out for us. So we've got 1 is equal to the probability of A plus the probability of B minus their intersection, add in the intersection of the complements. So it runs off the screen a little bit here, but that's what we have, right? So then when I move the slides along with this, so look here, what do I have? Well, I know the probability of A from this slide is 0.5. I don't know what the probability of B is. The intersection of the two is just told me to be, what, 0.1? And the intersection of the complements down here is told to me to be 0.3. So 1 is equal to, so I'm going to add up these values. 0.5 plus 0.3 is 0.8 minus 0.1, 0.7. A little bit more algebra, subtract 0.7 from both sides, and I'm left with the probability of B is 0.3. Okay. So all I'm doing there is using that equation. I know 3 of the 4 unknowns, plugging everything in, and after that, it's just a little bit of algebra, right? Just a little bit of algebra there, okay? Any questions on that before we keep moving? Are there any questions on that? So really, once we identify like that equation that we can use, it's just plugging in the 3 values we know, solving for the one we know. Now, the one thing I will say to be careful of, and last class we didn't go through this, but I think we have a little bit of time. So actually, I'll work this one if you want, but I'll mention it in 1 second. So another way you could have done this, I don't think it's as easy, is you could have solved for first from this equation. You could have solved for the probability of B, so you could have moved everything over as unknowns. Then once you had an equation that was the probability of B, sorry, someone's delivering a package. So if you solve for the probability of B as a function of all these other things, you could then plug all the numbers in, and then you wouldn't have any algebra to do at the end. Personally, I think it's easier to do the algebra with the actual numbers, so I would always plug the numbers in first and then move things around. That's just me. But if you do it this way, you know, if you did the other way, you'd find the exact same answer of 0.3. So this other problem where it's very similar, right? So actually, you can kind of work off the same equation. I have this same equation written at the top. Now I'm just going to have different components. So I've got this same equation. Now I'm asking for what's the intersection of A and B. So I now don't know this. So I know that the probability of A is 0.3, right? That comes right from the slide. The probability of B is 0.3. I don't know the intersection yet. And then I know the intersection of the complements is 0.5. So I'll do a little bit of math, 0.3, 0.3, 0.5. So 1 is equal to 1.1 minus the probability of A and intersection B. At this point, if you can already see that, well, what would have to be subtracted from 1.1 to get 1 would be 0.1. But the algebra here, which is you can make an easy mistake, is, so let's say I go subtract 1.1 from both sides. I'm left with negative 0.1 here, but it's negative 0.1 is equal to negative probability of A intersection B. So sometimes I'll have people answer like -1 if they're solving for the intersection, but you have to remember, no, you need to get rid of that negative sign too. It's on both sides, so it would cancel out. And obviously, the answer to the probability, it can't be negative, right? The probability has to be somewhere between 0 and 1. So if you do make that mistake and forget that that negative sign is there, you should hopefully remember that property of probabilities, and you won't make that mistake if, say, one of these possible answers was negative 0.1. Instead of like 0, I put negative 0.1 in there or something. Okay. Any questions on that? Do you want to see the board or anything that I just did again? I know that I did that one kind of quick. But if we look here, I've got kind of the work up here as well for that sample question, just another way of kind of looking at it. But I did the work on the board for you as well. No questions? So next class, we'll start talking about multiplication rules and doing some more things with independence. We might briefly start to look at an Excel file, which it'll be up there on Canvas, called Union Data. So be prepared Wednesday if you are showing up in class, which, like as I mentioned, I believe I said what should be Group 1 Wednesday and Group 2 Friday. I'll get an announcement on Canvas about that. If you want to bring your laptop to work along, that'd be great, because we might start doing a little bit of Excel work with that Union Data to see how we can take data, right, and create our own contingency tables. Like, I'm just giving you, let me see, scroll down a little bit. I'm just giving you all these numbers. Where would they actually come from if A and B actually were some real things that we could have data on, right? So we'll take a look at that. I think on Wednesday we might towards the end, because we need to get through this independent stuff. I've got some other fun stuff here that we could work through. I got some additional things I might bring in on Wednesday as well, but we will definitely get to do some Excel work on Friday, and hopefully at least start it on Wednesday. Okay. Any questions for me as we kind of end class here? Nobody? See people leaving already. So, all right. Well, I'm going to end class on that. If you do have a question, I'm going to leave Zoom open for a little bit, and I'll have the chat open. And if you want to or kind of talk, that's fine as well. See some of you on Wednesday. See some of you on Friday.